data processing and how it evolved, right? So today we are going to work with, or not going to work with, but to discuss, right? How was data, transformed and processed traditionally? Then what happened and how Hadoop came into the picture? What Hadoop changed? One second, it's being recorded. Yeah, what Hadoop changed into the system, right? Then what were the limitations of the Hadoop ecosystem that we had to introduce something called as an Apache Spark, right? Followed with trying to understand the architecture of Apache Spark in very clear and easy manner, right? Now, before the advent of Hadoop, right? Your traditional environments. So traditionally, what happened was before this Hadoop and the modern big data frameworks came into the picture, data was processed, largely, or data processing was largely dependent on centralized systems, all right? Single systems, relational databases, all right? These systems, were effective for structured data and to an extent, moderate volumes of data. Yeah, all right. Yeah. So as I said, traditionally, right, uh, we were processing the data in a centralized architecture. All right. When you talk about centralized architecture, what that means is that data was typically stored and processed on a single server. All right. So data was stored in a single server. Data was processed on a single server. All right. Sometimes on a single server, sometimes on a small cluster of some high-end machines, right? But this centralized approach, meant that all computation and all storage, right, uh, they were bound by the capacity of your single server. All right. So this server would have some capacity in terms of compute and storage, and that became our maximum limit when we were trying to process the data, right? Because to process the data, you need two things. One is compute power so that you can process the data. The second is the storage ability to store that massive amounts of data. Correct?
Sorry to interrupt. What is it compute means? Like exact meaning?
Compute means compute is a term used for CPU and RAM. All right, compute power means some processing power and memory. Clear?
Yeah, thank you.
In cloud computing, generally the word compute is used for CPU and RAM, right? That is why we say compute based resources. So, what are compute based resources? Virtual machine is a compute based resource, app service is a compute based resource, container is a compute based resource, right? Why? Because all of them require some amount of CPU, some amount of RAM. All right. That is why when we create nodes in a distributed architecture, we call it as a compute cluster.
So, yes, what is this AS? What does it mean?
AS is app service.
Okay.
So within Azure, right, there are many services that help you do a lot of things. App service is another such service that lets you host web applications. All right. So you know what goes into hosting of a web application? A lot of things. You'll need some compute, you'll need some storage, you'll need some custom domain features, some scalability features, some backup related features, right? So all of that is present within this single service. So if I create an app service, I can go and host my application using that app service plan. All right. Now, uh, as I said, these systems and the processing of data was very much dependent on a single machine. And now that is where the problem in any infrastructure lies. If you rely heavily on a single machine, it's very dangerous, right? It's very dangerous because that is a single point of fault. If anything goes wrong in that single machine, your entire infrastructure crashes. All right. So these systems, these centralized systems, right? As the data volume increased, these systems or these models, became a bottleneck due to their limited compute and storage resources. All right, we used to call them the monolithic systems, right? Then we had relational database management system also, RDBMS, uh, like Oracle, MySQL, the SQL server that we have. They were also the backbone of data processing, right? And they used you only no they used to store data in a structured format, right? In the form of a table. Structured data is a data which is stored in a form of a table where you have predefined columns with fixed data types, and each new entry or each new data is a new row, right? So these your relational databases, right, or the RDBMS systems, they use something called as SQL to query this data, all right, or the SQL, which is your structured query language, to manipulate the data, to retrieve the data, to process the data. Now, these RDBMS systems, they were optimized for transactional processing, correct? What is transactions? Individual operations that you used to perform. Create, update, delete. Yes. So these were all your different transactions, the CRUD operations, right? And what do you do with a database? You add new rows, you delete rows, you modify rows. So these are all individual transactions that you're doing on the database systems. And that is why these systems are also known as transactional systems. All right. And there is another name given to these systems. Can you tell me? Systems which are optimized for transactional data processing.
Online
Oh,
analytical process.
absolutely correct. We call them OLTP systems. Online transactional processing systems. All right. Now, these OLTP systems, they were optimized for transactional workloads. They were optimized to, having a lot of operations happening on the database at a single time, multiple operations, multiple transactions happening. And these systems were, created to efficiently handle those transactions. But what this system could not handle was analysis of data. Why? Because analysis requires compute, processing of data. All right. When I say analysis, I want to process this data also. It requires compute. And if I try to do that analysis or processing of my data in an RDBMS system, that would strain the entire database. All right. That will hog up the compute that the database has. So that is why your transactional systems, they were not optimized for analysis. All right. And these RDBMS systems, they had some limitations also in terms of scalability, right? Uh, Vertical scaling. I think we saw yesterday what vertical scaling is. To add more power to the single machine was very expensive, and it had some physical limits also. There is a limit up to which you can expand, right? Beyond that limit, you cannot. So there was a limit to the scalability here. Flexibility was also an issue. They were not well suited for unstructured and semi-structured data, right? Whereas if you look today, right, majority of your data is unstructured and semi-structured data. Do you agree with that? Majority, 80-90% of the data getting generated today is unstructured or semi-structured data, right? So the RDBMS systems cannot handle that because they are, storing the data in a structured format. So only structured data could be stored there, data present in the form of tables, right? So that was an issue. Now, also, batch processing of data in my RDBMS systems was inefficient and very slow. All right. After that, we started creating these ETL pipelines, all right, or the extract, transform, load processes were used. And they were used to move data from various sources into a data warehouse, right? And these pipelines were often built using tools like Informatica, Talent, or custom scripts in language like Perl, Python, right? And the process was very simple. You extract the data first from wherever the data is stored at, right? That becomes your source of the data. Then you transform the data, you clean it, you normalize it, you enrich the data, you apply the filters, you apply the aggregation, right? Based on your requirement. And then you load this data to a destination, right? That is the core definition of ETL. Get the data, transform it, load it, right? Loading means inserting this processed data into a data warehouse for analysis purpose. Because once you've transformed the data, it is cleaned, it is ready for analysis. And all of this data was kept in their data warehouses, right? And we had, you know, traditionally we had data warehouses like Teradata, IBM D2, right? They were used for analytical processing. And that is where we got introduced to a new term called OLAP systems. What is OLAP? Anyone?
Online analytical process.
Online analytical processing. Now, this was different from your OLTP systems. How? Because here you could process the data, you could analyze the data, you could do analysis on the data. And these data stores, your data warehouse specifically, they were created so that you can do the analysis of data, right? What is a data warehouse? Data warehouse is a place where you keep or clean data and you want data analysts to come and work on that data there. It means that it was optimized for analysis, right? This is where it supports, your data warehouses will support complex queries, complex aggregations, but they were expensive, all right? And they required specialized hardwares, and scaling them, right, to handle the growing data volumes was also challenging. Now, while some parallel processing was possible back in the day using some multi-threading or distributed databases, but it was not as seamless or as fault tolerant as the modern systems that you see today, right? Failures of any sorts mostly required manual intervention, and data recovery was a big headache, right? In the early times. Then another problem with the early time was that you had file-based processing. For very large data sets, organizations would sometimes use files-based system, right? CSV files, XML files. They will keep their data over here. And these file-based systems, they processed the data, right, using custom scripts. So this approach, it lacked certain level of standardization, it was error prone, and it was difficult to maintain, right? So in conclusion, your traditional data processing was effective for its time, right? At the time where we had limited, unstructured and semi-structured data, because in the early times, most of the data that we used to store was in structured format only, right? But then it lacked scalability, it lacked flexibility, there was no fault tolerance there, right? Fault tolerance as in there is a single machine. If that machine fails, we are gone, right? And it was not meant to be for modern big data problems, right? And modern big data problems are defined by three V's. Have I told you what those three V's are? There are three V of the big data problem. These three V's are volume, variety, and velocity. This is currently the problem that data engineers have to solve. How do I manage the sheer volume of data that is getting generated today? We are generating massive amounts of data on an hourly basis, all right? On an hourly basis, let alone the day, the week. Every hour we are generating huge amounts of data. So this huge volume needs to be analyzed, because now organizations don't want to make any decision which is not based on data. Today, if you see players playing football and cricket, you will find data analysts in their team also. Have you seen that? Today in sports team also, they will have some data analysts who will try to, gather all sorts of data and then try to analyze the performance. So you think about big major corporations, how much data would they require to study their business, to study their competition, to study the market that they're working in, right? To study the consumer behavior. So a lot of data is required, and all of this data that is getting generated, it needs to be analyzed. There is something is always there in any data which is getting generated, all right, or some importance is always there, right? So how do I manage the volume? The second is, how do I manage the variety of this data, right? It is coming in all sorts of forms, right? I'm getting structured data also, I'm getting unstructured data also, I'm getting semi-structured data also. So my solution, the big data solution that I'm trying to create, all right, or whatever solution I'm trying to create to address these three V's, it should first of all be able to handle the volume. Then it should be also able to handle the variety of data. The solution should be able to process structured data also. It should be able to process semi-structured data also, and unstructured data also. If you don't know what semi-structured, unstructured, and structured data is, structured is your tables, the relational databases, where you have rows and columns. Semi-structured is your JSON data, XML data, and your unstructured data is images, videos, right? We sometimes call it as blob data also. What is the full form of blob? What is the full form of blob? Full form of blob is binary large objects. So this data is represented in binary format, in form of ones and zeros. All right. And with this, you know, uh, the problem that we were facing, right? That is where, or with the RDBMS, I told you, right? The scalability was a problem. RDBMS also had a very rigid schema. Yes or no? Would you agree to that? Changes to the schema would require some downtime and careful planning, right? It was difficult to adapt, or to the evolving data structures, and it was very poor. The relational databases were very poor for unstructured data. RDBMS struggled with unstructured or semi-structured data, right? Like your images, log files, sensor data, and all those things. So to you know uh, overcome these problems, we had the rise of Hadoop. All right. And that changed the entire data processing world, right? Before Hadoop, data processing was dominated by centralized systems, the relational databases systems, and whatever issues I told you, right? It was there. Then Hadoop was born out of the need to process massive data sets, right? When we defined big data, and what is the definition of big data, right? You need to understand that. If I give you a pinch of sand, a small pinch of sand, and I put it in your palm, and I ask you to count the number of particles, I know it will be hard, but will you be able to do it? A very small pinch of sand, if I give it to you. Yes or no? You might,
Yes.
right? You might eventually be able to, study, not study, basically, go through it particle by particle, analyze it, and, uh, you know, uh, count the number of particles there. But when you talk about, and I give you an entire beach, can you do it? Yes or no?
No, not possible.
Not possible, right? That is big data. So therefore, Hadoop was born to process this big data, right? Which is unimaginable. You cannot imagine how you're going to process this data. Massive data sets, right? And Hadoop was created to do this efficiently, cost effectively, all right? And it was inspired by a paper that Google published, right? on something called as a Google file system and the map reduce function, framework, right? So Hadoop was developed in around, I think, 2005 was the time. It was later adopted and open sourced, right? And eventually it became a top level Apache project. All right. It introduced a new model of distributed computing. All right. This meant that instead of relying on a single powerful machine, I was now running a cluster of inexpensive servers, right? And I was distributing the computation also, and I was distributing the storage also, right? So the Hadoop's architecture is built around two fundamental components. The first thing is called as HDFS. All right. The first thing is HDFS, which stands for Hadoop Distributed File System. All right. HDFS is a distributed file system which was designed to store large files. All right. And these large files were stored across multiple machines. So HDFS results in distributed storage. I'm not going to store all of my data in a single place. I'm going to break that data into smaller chunks, and then I'm going to store it across multiple machines. It breaks files into, blocks. It calls them blocks. Each block, typically is of the size 128 MB or 256 MB. And then these blocks are distributed across the cluster. Cluster, you understand? In distributed computing, we have many machines. These machines are called as individual nodes. All these nodes are together called as cluster. So when I say I am distributing my data across the cluster, it means that if this was the data that I have, I broke it into multiple pieces, right? 1, 2, 3, 4, and 5. And first data came here, second came here, third came here, fourth came here, fifth came here. Like this, I have distributed it across the cluster, right? So within Hadoop, we had now fault tolerance. How? What did fault tolerance mean here? Fault tolerance meant that, each block was replicated. This block that I'm telling you, right? Data was divided into smaller blocks, and each of this block was replicated 3 times on different machines. 3 copies of each block was created. And that is something that you'll find in Azure everywhere. At least 3 copies of your data is created all the time. Even today, you go to Google Drive, all right, and you store your data there. All right. Have you ever heard Google coming back to you and telling you that, sorry, we have lost your data? Has it ever happened? Have you heard it? Right? Have you heard ever that Google came to
No.
somebody and told them that,
No.
sorry,
No.
we stored your data in a server and in a storage device in some location, and that location caught fire, there was a disaster, there was an earthquake, there was a tsunami, whatever it was, a flood, and sorry, your data is gone now. Never gonna happen. Never.
No.
Why? Because even a small file that you upload to Google Drive is replicated into 3 copies. Always remember. You'll have a copy near to you. You'll have a copy somewhere else also. You can have, how the copies are arranged, that is internal to, Google's discretion. You don't get to decide that because you are not going to decide how many copies are getting created. But then always remember 3 copies are created. Even in Azure storage, all right, that we will see in next week, what Azure storage is, how it works. Whenever you store your data or you upload any data, the least, and whenever you upload a data, and for your storage account in general, you have to select something. There's a configuration called replication strategy, right? What does replication strategy means? Replication strategy means how your data will be replicated. So there are different ways in which your data gets replicated, and the most basic is LRS. LRS stands for, and don't worry if you do not understand it right now. I'm just giving you an example. When we talk about Azure storage, you'll have a much better understanding at that point. So whenever you create a storage account, there is something called as a replication strategy that you have to define. There are multiple strategies: LRS, ZRS, GRS, GZRS, RAGRS. All of these are different strategies. Now, when you talk about LRS, you say that 3 copies will be created, and you cannot select anything below LRS. LRS is the least. So in the least, I'm saying 3 copies will be created. So that means whenever I'm storing a single file on cloud or on Azure, 3 copies are getting created by default. So that was the benefit of the Hadoop file system. Now I had copies of my data. These copies were spread across different machines. So if any of the machines failed, guys, can you please all mute yourselves? Wait. Yeah, thank you. So as I 3 copies are getting created, and they get distributed on different machines inside the compute cluster, right? So if any of the machine fails and my data on that machine was my, whatever data was there on that machine, right? It's not like I'll never get that data back again. I'll still have 2 other machines inside my cluster where my data will be present, right? So that introduced fault tolerance, replication across different nodes. If one node fails, data is still accessible, and it gave very high throughput. All right. This was optimized for large sequential reads rather than random access. All right. And new nodes could be added easily without any downtime. All right. I can bring these new nodes anytime I want. So that gave this HDFS a lot of popularity, the Hadoop distributed file system, where I was storing my data that needs to be processed. The second thing that Hadoop introduced, right? I told you 2 things were introduced. One was HDFS, the other was the framework that is called as the MapReduce framework. All right. So MapReduce is a programming model. All right. MapReduce is a very simple programming model, which can process large data sets in parallel. So now you are doing parallel processing of the data, and it contains 2 phases. Phase 1 is the map phase. Phase 2 is the reduce phase. Map phase says that whatever data is incoming, right, it is distributed on different machines to be processed. That is the mapping or the map phase of the MapReduce programming model. All right. So you process the input data by dividing it into multiple smaller chunks on different machines. That is the map phase. The reduce phase is once the processing is done, right? Once the processing is completed, you combine all the individual outputs together, right, to get the final outcome, and that is the reduce phase. So when you have the big data as in a small, let's say, a chunk of data, and you pass this data along with the code, right? Because when you are having the data, you also need to define the logic that you have to perform, right? The transformation that you have to perform on this data, and that was defined generally through the code that you had written, right? The code will define what you need to do with the data. So this data along with the code was shared over here. 1, 2, 3, 4. Code was there, code was here also, code was here also, code was here also, right? So all these individual nodes had the code, and they had the, along with the code, they had the data. So this will produce output 1, this will produce output 2, this will produce some output 3, and this will produce output 4, right? Based on the data that was shared, the output will be performed. But this cannot be your final data. I cannot give 10 output files. I need a single output file. What I do, I'll combine them in a logical order, and I'll have my final output. So this distribution of code along with the data was the map phase. The combining of the result towards the end was the reduce phase. Is that clear to all of you? Yes or no?
Yes.
So now we had parallel processing in place. Tasks are distributed across different nodes and executed in parallel. Now we had fault tolerance. Yes. and computation is moved to where the data resides. All right, we are not sending the data somewhere and then processing it all in a single place. No, computation will be done on whichever node the data has been sent to. Clear? So traditional limitation of scalability, how did Hadoop address it? Hadoop enabled horizontal scaling. All right, add as many servers as you want, increase the size of the cluster as needed, right? And the systems would grow based on our data growth, right? So scalability was a problem in traditional systems, addressed by Hadoop. Fault tolerance was a problem with traditional systems. Hadoop addressed that also. Cost was a problem, right? Traditional systems, they required very high-end servers and expensive licenses. Hadoop, ran on commodity hardware. It was open source, right? So drastically reduced the cost. And traditional RDBMS, it required structured data with predefined schema, whereas Hadoop could store and process structured, semi-structured, unstructured data, logs, images, videos, JSON, XML, everything it was able to process. And the processing speeds were very high. All right. Traditional ETL jobs were slow and batch oriented, whereas the MapReduce enabled parallel processing, right? Significantly reducing the job completion time for very large data sets. All right. And as and when Hadoop grew, it created an ecosystem, a Hadoop ecosystem. All right. It created a rich ecosystem of various tools that emerged to address various data processing needs. Right. You have Apache Hive that would give you a SQL like interface to query your data stored in HDFS. Right. And it made Hadoop accessible for analysts who were familiar with SQL. You had Apache Pig, right? Again, a high level scripting language for data transformation, right? And simplified the complex MapReduce jobs. So writing your MapReduce functions, right, or the code was very complex task. That is one of the shortcomings of Hadoop, that writing MapReduce code is very complex. All right. So a lot of different, I would say in the ecosystem, the Hadoop ecosystem, different tools came in, and in the real world, Hadoop had a very big impact, right? Banks were using it to detect fraud. Healthcare, providers were processing data for personalized medication and drug research. They were doing that with Hadoop. Telecom companies were monitoring network performance, predicting outages, right? Social media platforms were analyzing the user interaction and the trends. And companies like Facebook, LinkedIn, Twitter, Yahoo, they all built massive data infrastructures on Hadoop. All right. But then there were limitations as well when it came to Hadoop. A lot of limitations, right? First, batch oriented. MapReduce was not, could not support streaming analysis. Streaming data analysis means analyzing the data in real time as and when data arrives. No, we'll do batch processing. Very complex programming language, complex programming. Lot of latency, right? There was some high latency for very small and interactive queries also. All right. So there were some problems here, right? Uh, One more problem was that Hadoop was reading and writing the data to disk. There's a lot of disk input output happening with Hadoop, right? So now you tell me, if I am processing data and I'm writing the intermediate data onto a disk and then reading it for a subsequent operation, does that make my processing fast or slow?
It will be slow.
It will make it slow, right? Now, in your machines, do you know of any hardware that was introduced to avoid reading and writing data regularly from the disk? Any hardware that plays that role where you don't have to go to the disk every time and something could be temporarily stored nearby that could be accessed, quickly? Do you know of something?
Yeah, it may be cache, right? You can temporarily
It's your
store
memory,
the.
right? It's your RAM.
Yeah.
What do we do with RAM? Why is RAM required? We put intermediate result in the RAM. right? Any application that is currently open will use my RAM and stay there, right? I don't generally work with data directly into the disk. I don't put data directly to the disk. I don't read directly from the disk. That is a very slow process. So these were the limitations of Hadoop. And that is where came in Apache Spark, the best of all. This is the evolution beyond Hadoop. All right. We all know Hadoop revolutionized big data processing by enabling, features like distributed storage, parallel computation. But, and it also allowed organization to process, massive data sets using commodity hardware, right? I did not need specialized high-end hardwares. I could use simple machines, simple small machines, right? So it made big data analytics accessible. It made big data analytics affordable. But then there are a lot of limitations also, as we discussed, and that is why Apache Spark was born in around, I think, 2010, right? Uh, they created it. They, donated it to the Apache Software Foundation in around 2013 or 14, right? And it was designed to overcome all the inefficiencies of Hadoop's MapReduce method. All right. It wanted to maintain the core strength of scalability, fault tolerance, and distributed processing, but it did not want Hadoop's MapReduce. All right. And Spark introduced a completely new computing paradigm. All right. And this was based on something called as in-memory processing. So now I don't have to write the second, let me have a glass of water. Yeah. So now I was writing data in the memory. I was processing data by storing it in the memory. I was not reading and writing data directly from the disk. And that, improved the performance for many workloads. All right. So the first thing, in-memory processing was introduced. And it was the most significant innovation at that time. All right. It could keep data in memory between operations, right? Let's say if you want to do transformation 1, followed by transformation 2, followed by transformation 3. Now, after you're done with transformation 1, you will need to put the intermediate data somewhere. So where do I keep it? Disk or memory? Now, this would mean latency. This would be fast to write also and to read also. So that is why this intermediate data in between your operations was kept in memory, that reduced the need for disk input output. So in MapReduce, each stage, writes the intermediate results into the disk, and Spark, by contrast, stores the intermediate data in a memory using something called as an RDD, which we'll talk about later on. All right. As of now, don't worry about RDD, but just know that the data is kept in the memory. That is your RAM. Now, this made Spark, and some people say, and this is something that you will find everywhere, Spark is equal to Hadoop into 100 in terms of speed. What does this mean? It means that Spark was considered to be 100 times faster than Hadoop, but for certain workloads, it's not always true. All right, it's not always true. It is only true for a specific condition and a specific workload, a specific task that you had to perform. All right. Now, what Spark did was, it then introduced the concept of something called as an RDD also. RDD stands for Resilient Distributed Datasets. RDDs, which is, let me write it down. Sorry. Resilient Distributed Dataset. These are the foundational or the fundamental data structures in Spark. All right. They are immutable. They cannot be destroyed. They are distributed collection of data. All right. You basically create an RDD by distributing data across, multiple nodes, right? And one more thing about Spark was the DAG execution engine. DAG stands for Directed Acyclic Graph. This means that if I want to do transformation T1, T2, T3, T4, then Spark will not blindly start going from T1 to T2 to T3 to T4. It will create something called as a DAG for this execution. That is, it will try to optimize and see how the transformations have to be done, in which order it will be most optimized. All right. So transformations on RDDs are not executed immediately. Instead, Spark will build this, DAG. It will build this graph of operations, which will optimize the execution plan before running it. Let's say if running T2 first gives me a benefit and then T1, then T4, and then T3, then this will happen. All right. So before directly executing the data, Spark creates a DAG that is going to, first create an execution plan. So you create a plan first, then you go to execution. That is what Spark introduced. All right. And Spark gave you a unified engine, a single engine that is capable of doing everything. You want to do batch processing? Possible. You want to do stream processing? Possible. Spark streaming. You want to do machine learning? Possible. You want to do graph processing? Possible. You want to run interactive SQL queries? Doable. So it's a single place where you can do everything. All right. So you have Spark Core, which is used to, which is the foundation of the Spark platform, right? You have Spark SQL that allows querying structured data using SQL or a data frame API. We'll cover this obviously in depth. Spark Core, Spark SQL. We have Spark Streaming that processes real-time data streams. We have something called as MLlib, which is a machine learning library, and it includes algorithms for classification, regression, clustering. Right? If you do not know what these are all different machine learning workloads. Regression is when I want to predict something numerical. Correct? All of you know what regression is. Within machine learning, we say there is something called as regression, there is classification, and there is clustering. Right? So what regression does? It tries to identify a numerical value. Estimate tomorrow's temperature. It's a numerical value. Estimate this stock price 10 days from now. Numerical value. All right. Find out whether the given image is of a cat or a dog. Not regression. All right. Look at the picture. Give the name of the animal. Not regression, because here the output is not a numerical value. That is classification. If I show, or if I write down the features of a flower, and my AI model or my machine learning model has been created to identify the species of the flower based on the features, then that is classification. I can tell between different species. An incoming mail is a spam or not. It's not regression, it is classification. You classify it as a spam or not a spam. Clear? And clustering is when you try to group similar data together. All right. So Hadoop had limitations. Spark addressed those limitations. Now you had, limitation in Hadoop was high disk input output latency. Spark introduced in-memory processing, right? Hadoop was inefficient for iterative tasks. Spark solutions was, it introduced caching and DAG execution that would create a proper plan first, and it was very well suited for iterative tasks. Hadoop had complex programming. Spark, gives us high-level APIs in Scala, Python, Java, and R. These APIs, what they mean is, if I want to talk to the Spark architecture, if I created the Spark architecture, right? And when I say Spark architecture, it consists of a few components. So when I create this Spark architecture, I should be able to contact or communicate also with that. If my task is to process data, so I should be in a place to tell Spark that, listen, this data needs to be processed and this is what I want. How do I tell that? I can tell that using any language, right? And the language here is called as API. So I can use Scala also to talk to Spark architecture. I can use Python also to talk to the architecture, to the compute. I can use Java also. I can use R also. In Hadoop, there was no real-time processing. Spark introduced Spark streaming or structured streaming within Spark. Hadoop had a rigid execution model. Spark has a flexible DAG-based execution engine. All right. So these are all the benefits of Spark, all right, that you have over the Hadoop ecosystem. Is that clear to all of you? Yes or no? Now I'll quickly give you a quick insight of what the Spark architecture is like. So you have something called as a driver program running on the driver node. So you'll have a driver. Your cluster will contain of one computer that will become the driver and the rest will become workers. All right. So driver is the heart of the Spark application. It will run the main function and it is responsible for converting the code that I am going to write into a DAG, right, of tasks. It is going to schedule tasks on these individual machines, right? And it is going to complete the execution and collect the final output result. So the driver maintains, the information about the Spark application state. It communicates with the cluster manager. It communicates with the executor. Then these are executors or workers. All right, you can call them workers also. You can call them executors also. You can call them slaves also. And driver could also be called as a master, right? So this follows a master slave architecture. The master will give instructions and the slaves will do it. So executors are the workers that process, right? Or executor are the processes that run on these nodes. All right. So inside this node one, I'll have executor process. Over here also I'll have an executor process. Here also I'll have an executor process. And these executor process will run tasks assigned by the driver within the computer. They will store the data in the memory, right? The executor processes will store all this data in the memory and they will, report the task status and the results back to the driver. So how does this communication happen? Does the driver talk to each of these slaves or the workers? No. They have something called as a cluster manager in between. All right. Job of the cluster manager is to manage all these workers. All these workers, whether they are in a working condition, that means they are processing data, or they are left idle, or they are not ready to start. Right? When I say not ready to start, basically they have failed. They could not be started. So cluster manager will keep an information of all the workers and it will report that to the driver. The moment any of the executors, right, or any of the worker here or the worker node is now empty, it does not have any task. Cluster manager will get this information and cluster manager will ask driver that I need more tasks, right? I need more data, right? Because the data is going to be processed in memory. All right. Memory size is limited. If I have 10 TB of data, right, then I might send, let's say if over here in the memory, I only have 1 GB data available, 1 GB memory available for processing. So I can only process 5 GB at once in parallel. Once this is processed, then I'll have to process 5 GB more. Once this is done, then I have to process 5 GB more, right? So like that, it will go. Obviously, if I want to process more data, then I'll increase the number of nodes and I'll process, let's say if I have 100 nodes, so I can say 100 GB in a single cycle was processed. But then the driver has to, it cannot process all the data at once. If you create, 1,000 chunks of your data, it does not mean that you'll have 1,000 nodes to process that, that data. It could mean that you have a limited number of nodes, and these nodes, once they process the data, they'll send you the output, they'll get new data, they'll process it, they'll give it again, they get another data. So like that, it keeps on working. Cluster manager, there is a standalone cluster manager which is used within Spark. Standalone cluster manager is Spark's default cluster manager. And we talk more in depth of this. All right, I'm just giving you a high level picture of the architecture. Right? The standalone cluster manager is there. Hadoop used something called as Yarn. Yarn is also a cluster manager that was native to Hadoop. This is called as yet another resource negotiator. Now, do you know of any other cluster manager? Does anybody know of any other cluster manager? It is widely used in programming today. It is used to manage cluster nodes. Anyone knows?
Kubernetes.
Yes, Kubernetes.
Yeah, yes,
So
someone
Kubernetes is
yesterday
also,
told.
yeah, Kubernetes also is a cluster manager.
Yeah.
All right. So you can use any one. If you want to use Yarn, you can use that. If you want to use Kubernetes, you can use that. There is something called as Apache Mesos also. You can use this also. But by default, standalone will be there. If you do not specify anything, the standalone cluster manager will be there. All right. So with that, we'll stop here for the day. And this will end the demo sessions that we had. And from Monday onwards, we'll have regular sessions. We'll start again from the basics, right? Obviously, some of it we have already discussed, but then again, we might see some new faces who, in the first class who may not have attended the first demo session or the second demo session. And we'll start with Azure basics. We'll cover first week, we'll do the Azure, and then we'll switch to completely Spark and Databricks. And then we'll see all the different capabilities of Databricks and Apache Spark in general. All right. So please, make use of this opportunity. If you've already registered, I'll see you on Monday. Those of you who've not registered, right? I encourage you to please register and be a part of this training session. From Monday onwards, only people who have registered will be the part of the training. All right. And I would like to thank all of you for being patient with me and attending this 2-day demo session that we had. I just gave you a brief introduction into what we are going to study. But as I said, this is just the tip of the iceberg. And we have a lot to cover, a lot of topics to cover, a lot of tools to discover, and we'll do that starting Monday. All right. So thank you everyone for being here, being a part of this demo session. It was really nice having all of you. You're all very interactive, and I hope to see you guys on Monday.
Shreyas, I
Thank you
think
very much.
a couple of questions we have.
Yeah, yeah.
Please
I'll take
ask
the
your
questions. Yes.
question.
Shreyas, like with this training, right? You'll be covering PySpark also?
Yes, we'll see. We'll be starting with and we'll cover the basic part also, and the I would say the difficult, some difficult scenarios also we'll see, but complex ones. But yes, PySpark, you will have a good understanding if you just attend this course. You can build a good understanding on PySpark.
Okay,
I'll
so
show you
you
step by step how you can
uh-huh.
read data, how you can write data, how you can transform data, right? Once reading, writing, and transformation is clear to you, then whatever we do with the data, you'll understand it very clearly.
Okay, and do you explain like the migration part, like from on-prem to cloud?
Migration is not required here as such.
Not really.
Yeah.
Okay, okay. So what kind of jobs we can apply full total on Azure Databricks only, right?
Yes, anything that requires data engineering and data bricks has been mentioned as a required skill, you can apply for it.
So, okay, overall, how many years we can show up with this training?
Post the training completion and post the project completion, you can easily show some 2 to 3 to 4 years of experience based on how much you practice. Obviously, the more you practice, the more years of experience you can show. The more projects you do, the better experience you could show.
Okay, so at least minimum 2 to 3 years we can
Yes,
show up.
yes, absolutely.
Shreyesh, I have a quick question here. You told us right, Python and SQL. You should have some basic knowledge to learn this
Mhm.
Azure.
Yes.
SQL, yeah, being a ADW resource, I have hands-on experience in SQL, but
Hmm.
Python, I can claim it as a zero. So if I
That
go
is
through
what.
some
See,
basics next
yes,
to
basics are more than sufficient. Absolutely.
yeah, because if anything asking right to like to write any scripts or something, I don't have any experience in Python.
Not
That's
required. We'll not be writing extensive scripts, but yes,
uh,
when we work with PySpark, I'll give you a very guided, detailed plan on, and it will be very logically created.
okay.
So the
Any
first thing that
suggestions
is,
or any link
hmm,
for the classes to to understand basic level for this particular Azure course purpose? Any particular link or class
see,
educational video you can suggest?
Python you don't need to learn Azure. Python you would require, to uh, build yourself in PySpark. All right, to be able to understand how this PySpark code works, and eventually for any data engineer, Python is a must, right? Today or tomorrow you have to learn that,
Okay.
right? So you better start today.
Yeah. Fine. Yeah. Sure. Thank you.
Hmm. Yeah.
Where can I register? The website
uh,
only, right?
Yes,
you
you can
can get
register through the website, or please reach us to the WhatsApp number. So, are you in any of our group, or can you share
Not
your number in
not
this chat?
possible. Uh, okay,
Yeah, I will contact you. Please share your number.
okay.
you can send a direct message. Yeah.
Yeah, Supriya, I think you have some question. Can you please ask?
Yes, it's a quick question actually.
Mhm.
What happened? Some of the banks, like they have a very sensitive data or restricted data. So, what they are doing, they are introducing their own cloud or internal cloud, something like that. So,
Mhm.
in that case, they cannot upload the data directly on any cloud like AWS, Azure, or GCP, something like that. They need lot of permissions. So they have introduced their own cloud, and can we use the same language, Databricks or PySpark, whatever, to onboard our whatever ETL tools we are using? They are not capable of processing the high, huge data. So can we use the same language to move that code on premise cloud?
Uh,
I mean, this tech skill set,
Let
I
me
would.
rephrase your question. So you said that banks have, sensitive data and they're having their own cloud. They're creating their private cloud, right? Essentially.
Correct, correct. Yes,
And they
yes,
have
yeah,
their own data, which they're, keeping and storing it on their private cloud. They're not storing anything on the public cloud,
correct.
right?
Yes,
Uh,
yes, yes.
Now, what is the question after that?
Yes, yes. My question is, now currently we are using like other ETL tools like Informatica, Data 360 and something like that. But now these
Hmm.
tools are not capable of processing huge amount of data. Like 1 GB of data process, it takes 1 hour. And now if data increases to 3 GB, 4 GB or
Hmm. Hmm.
more
Hmm.
than that, it takes like 3 hours or something like that. So we want
Yeah.
to increase the processing capacity. So in that case,
Hmm.
can we use this same language like Databricks, PySpark? To
Yes,
we want to
totally right.
eradicate of the.
No,
Mhm.
no.
Okay.
See, it's available with public cloud, that is there, but it is also
Mhm.
available locally,
Okay.
right?
Okay.
The cloud integration is
Uh-huh.
there, but Databricks in itself as a standalone tool also exists that you can use.
Okay. Okay. Got it. Got it. Mm. Oh,
Yeah, I have
thank
one
you. Yeah.
question
Got
related to the course.
Hmm.
So you are going to cover everything related to Databricks, right? So after our course, we no need to go for any other courses.
Not in terms of Databricks.
Yeah.
You'll have a complete understanding of data engineering workloads on Databricks.
Okay.
Yeah. Hi, Shreyas.
Yeah.
Do you have offline classes available or only online classes?
Only online classes.
Only online. Okay, fine.
Yes.
And we are getting recorded session for each class, right? After, like, if
Yes.
suppose if
After
I
every
missed.
class. Yes.
Hmm.
Every class, the recorded lecture will be uploaded.
Okay, uploaded to YouTube, uploaded to your
No,
website.
the
From there
LMS
we can
portal.
access.
Yes, the website, LMS portal. So you'll have a lifetime
Okay,
access to that LMS portal. Yeah.
thank you.
So overall, it is for 25 days, right, Shreyas, if I'm not wrong?
No, we mentioned 25, but see, that is an estimate. But generally, it will take around 30, 34, 35 also it can go. See, it depends on uh, what kind of classes we are having. When I say what kind of classes, basically, the more interactive you are, the more classes we will
Mm-hmm.
have eventually, right? If you're regularly
Yeah,
asking
yeah.
questions, if you're regularly involved, we'll spend more time on addressing, doubts and queries. So the duration increases eventually. But then, as I said, 25 plus is what we mentioned. 25 plus is going to be Databricks dedicated and 5 are bonus for Azure. So 30 plus, so you can expect as it is from now itself.
So, Shreyas, this 25 days included the project also?
Project will be given towards the end. The project documents will be shared with you towards the end. 2 projects will be shared that you can implement in your free Azure account.
No, but you will not help us to implement that project.
I'll be sharing the guided documents. If in case you have any problem, you can always connect with me and we can resolve those issues. If there is any implementation related problems that you're facing.
Okay, thanks.
Are we going to get certificate on this?
Certificate from our side, it's not available. But if you want, so you
Yeah.
can apply for the Databricks certification, which is available.
No,
Okay.
institute certificates are not valid.
So Databricks here will have their own
But
certificate.
if you want, we can give you the certificate. I mean, course completion certificate.
Okay.
So, Shreyas, I did earlier also one program with NIC, so
Mhm.
with Chandra sir. So,
Mhm.
Chandra gave us a few questions related to that to the certification. So, do you have questions also for the certification of
Yes, I'll be
Databricks?
sharing the exam terms with you, but that will be for the Databricks certifications. Yes.
Okay, thanks.
See, standalone Azure Databricks certificate does not exist, but Databricks certificate exists. All right then. Thank you all. I hope to see all of you on Monday. Thanks a lot, guys.